Okay, for this next video, what we're going to do is we're going to talk a little bit about arbitrary triangles, so not necessarily right-angled triangles. And it turns out that there's also a lot of interesting formulae that relate the sine and the cosine of the angles with the sides of the triangle, but they're a little bit more complex because the triangle is also more general than just a right-angled triangle. So the first formula that we're going to see is the law of sines that you have here on the top right. And the interpretation here, I'm going to make a drawing again, is you have an arbitrary triangle, not necessarily a right-angled triangle. And we have the angles alpha, beta, gamma. And then the sides, the opposite sides, A, B, and C. And what the law of sines tells us is that basically these three proportions are equal. So in each case, it's the sine of one of the angles, alpha, divided by the opposite side. And we do that for every angle, beta, and every opposite side, B, and then also gamma and C. So it's a very useful formula. You will use it in that form, but let's have a quick look and see how we can derive it. So proof. I already mentioned that this is not a right-angled triangle, but let's try to make some right-angled triangles out of this triangle. So what I'm going to do is I'm again going to draw a straight line down here, perpendicular to the base. And what I get now is I get two nice right-angled triangles, 1 and 2. And so let's look at each triangle separately. So if I look first at triangle 1, and actually let me call this side, the length of this perpendicular, let's call it h. So in triangle 1, what I see is that the sine of alpha is equal to h divided by b. And if I look at triangle 2, I get that the sine of beta, so remember the sine is always the opposite side divided by the hypotenuse, so that's in this case h divided by a. So from this I get that h is equal to b times sine alpha. From this I get that h is equal to a times sine beta. And now if I put these two together and I eliminate h, I find that b sine alpha is equal to a sine beta. And now if I divide both sides by ab, I get that this is sine alpha divided by a sine beta divided by b. So in order to go from this to this, you divide by AB, and since these are the sides of a triangle, they're different from 0. So that gives us half of our formula. It gives us this part. But now let's prove the other half as well. So again, I don't know anything about arbitrary triangles. I know about right-angled triangles. So let's make another right-angled triangle somewhere in our starting triangle. So that other right-angled triangle is a little bit more difficult to spot, but what I'm going to do is I'm going to extend this side like this and then draw another perpendicular like this onto that side. Obscured a bit by the title, so let me make it nice and clear like this. So we have a right angle here. And so let's have a look now at what we can do in triangle 3 here. So let me call this side K. And if I look at this angle right here a bit, I see that this is pi minus gamma. And so in triangle 3, I have that sine of pi minus gamma is equal to, again, the opposite side divided by the hypotenuse, that's b, so k divided by b. And I know from my trigonometry formula that this is just sine of gamma, so this formula tells me that k is equal to b times sine gamma. And now I have to relate that somehow to sine of beta. And in order to do that, we're going to look in the entire triangle. So if I make it a bit messy, I'm going to take this whole thing, like so. Everything that's lined up in blue. And we're going to call that triangle number 4. And so in 4, if I want to make the colors here correct, this should have been green 3. What do I know in 4? Well, if I look at the sine of beta, I have sine of beta is the opposite side, that's k, divided by the hypotenuse, that's c. So I get sine beta is k over c, or k is equal to c times sine beta. And now again, we can put these two together to get b sine gamma is c sine beta. And if I divide that by b times c, I get sine gamma divided by c is equal to sine beta divided by b. And that gives us the rest of our formula. It gives us this. Okay, very useful formula. Let's use it to compute something. And what we're going to do is we're going to work through a couple of problems, and in each case, these are problems of the form where you have two sides plus one angle, or you have two angles and one side, and you want to find the rest. So if that's the situation that you're in, that you have 2 plus 1 of either kind, then you can use the sine formula. So here, let's take, for example, following triangle. I have an angle here that's 20 degrees. I have that the side C is 804. I have that the angle gamma is a bit too small, gamma 25 degrees. And what I want to know is the length of the sides A and B. So here I want to find A and B. So if I look at the triangle, then there's one pair of sine and angle that I know everything about. It's C and gamma. So let's start with those two. So I have sine gamma divided by C, and that's going to be equal to something. And now, well, I don't know anything about beta, and I don't know anything about B, so let's put those aside for a second. But I know alpha here, and I want to find A. So I know that this is sine alpha divided by A. Now let's plug in the values that were given. So we have sine 25 degrees over 804 is equal to sine 20 degrees divided by a. And if I simplify that a little bit, I get that a is equal to 804 times sine 20 degrees divided by sine 25 degrees. And these are, of course, values that are not in your table, so you can't look them up. But if you use a calculator or some piece of software, you'll find that a is approximately 651. So that gives us our first answer. So now let's go and have a look and try to find b. So, okay, let's call this case A. And then for B, well, the first thing that we'll do is we'll try to find what this this angle beta is. So for beta, I know that beta is 180 degrees minus alpha, that's 20 degrees, minus gamma, that's 25 degrees. And so you get that this angle is equal to 135 degrees. So that's good because that's a nice angle. That's one that's in our table. So now we can take the formula again. So let's take sine alpha divided by, or rather sine gamma divided by c. And now that's equal to sine beta divided by b. So sine beta divided by b. Let's plug in everything that we know. So we have b is equal to c times sine beta divided by sine gamma. So that's 804 sine 135 degrees sine 25 degrees. And if you work that out, you calculate it, you get that this is approximately, so it's not an exact number, but it's approximately 1345. So that's one example, and it's typically how this formula works. But now the next thing up is there's a couple of ambiguous cases that you have to be aware of. If you're warned about them, you can usually spot them, but you have to know about them. So in order to see these ambiguous cases in action, let's just work through a couple of examples. So for the first one, I'm going to start with this triangle, where I have the two sides 7 and 7 times square root of 2. And I have that this angle, let's call it alpha, is equal to 45 degrees. And I want to know this angle. Let's call it, I don't know, let's call it gamma. So you say, well, okay, I have an angle and a side here, and I have another side, and I want to find gamma. So I can use the sine formula, that's correct. So let's plug things in. Sine 45 degrees divided by 7 square root of 2 is equal to sine gamma divided by 7. We work that out, we get sine gamma is equal to 7 times sine of 45, that's square root of 2 divided by 2, and this whole thing has to be divided by 7 times square root of 2. So if you cancel the 7 and the square root of 2, you're left with 1/2. This is great because this is one of the values that's in our table for sine. And now what we get is there are actually two solutions. Namely, gamma can be either 30 degrees or gamma is equal to 150 degrees. And what's going to happen here is, okay, we get two solutions, But now let's double check if both are valid or if one is invalid or if both are not valid. So let's start with gamma is equal to 30. So if gamma is equal to 30, let's compute the value for beta. So the angle beta is going to be 180 degrees minus alpha minus gamma. So that's 180 degrees minus 30 minus 45, or the other way around. So then beta is 105 degrees. That's great. And now let's have a look here. If gamma is equal to 150, then beta is equal to 180 degrees minus 45 degrees from alpha minus 150 degrees. And what you see is that we actually end up with a negative value. We get that this is equal to minus 15 degrees. And this is a problem, this is not allowed. Angles have to be positive, in a triangle at least. So we can rule out this solution. So the only solution that we have in this case is gamma is equal to 30, because if we calculate the other elements of the triangle, we get that the values make sense, they define a physical triangle. So we have here only one solution in practice. So that's the first ambiguous case that I wanted to highlight, and there's a couple more, so let's do another triangle. So now we're given a triangle with sides A is 26, C is 15, and the angle gamma is 29 degrees. So if we map that out, just to have something to look at, we get A is 26, C is 15, and gamma is 29. It doesn't matter where you put the angles and the sides, as long as gamma and C are opposite angle and side. So now let's compute some of the other properties. Let's in particular have a look here at this alpha and try to calculate it. So again, we take our sine formula. Sine alpha over A is sine gamma over C. We have all the elements. We know that sine alpha is equal to A 26 divided by C 15. Sine of gamma, that's 29 degrees. Okay, fair enough. Now if you calculate that, that gives you about 0.84. Again, not a value that you have in your table, so that's fine. If you press the inverse sign button on your calculator, or if you think a bit about the possible solutions, and we'll see more about that in the next lecture, you'll see that 0.84 gives rise to two possible values for alpha in our triangle. So either alpha is 57 degrees, or alpha is equal to 123 degrees. So this actually is equal to 180 degrees minus the 57 from over there. So we have again two candidate solutions. Let's try to see if one of them is unphysical, or maybe both of them are unphysical. So let's calculate, in this case, the remaining angle beta. It's again 180 degrees minus 57 degrees minus 29 degrees. And that gives us 94 degrees for beta. On the other hand, if we take 120 degrees here, we have beta is equal to 180 minus 123 degrees minus 129 degrees, and that's 28 degrees. So in this case, both values for beta, they're perfectly reasonable angles, and you can't rule out one or the other. So in this case, you actually have two valid solutions. So you always have to be a bit careful, especially if you calculate quickly. Maybe you find one of the solutions but not the other one. But think about, hey, is there maybe another solution hidden? And this other solution here comes from the fact that if I calculate what angle corresponds to sine value 0.84, I have to keep in mind that there's two possible angles. So in the next lecture, we'll see a specialized way to solve arbitrary equations of this form, and then that'll make it a bit more clear where these two angles come from. But for the time being, think a little bit about the fact that, well, if you have an angle alpha and you take the sine, that's the same thing as taking pi minus that angle, or 180 degrees minus that angle, and taking the sine. So either way, you get two valid solutions here. And then one last ambiguous case. It's also interesting. So I'm not going to draw the triangle here, but it's a variation on the same thing. So let's take alpha here to be 42 degrees. Let's take A to be 70 and B equal to 112. And again, we want to find beta. So we know this, we plug it in our sine formula. Sine beta over B is sine alpha over A, or sine beta is equal to 112 divided by 70 times sine 42 degrees. And if you calculate what that value is, you get that this is approximately 1.07. And this should set alarm bells ringing, because this is again an unphysical value. The sine and the cosine, they always have to be between -1 and +1. So if you have something that's greater than 1 for the sine, it means that that equation has no solutions. So here, let me put this in red just to emphasize it. So we have to have for all angles theta, we always have that sine is between -1 and +1, and so is cosine. And if that's something that is a bit new for the first time, then think about when we graphed the function sine and cosine, what they look like. In either case, let's draw sine. You have sort of this oscillation like this, and so on. And the maximum value here was +1, and the minimum value is -1. So sine and cosine always oscillate between -1 and +1. So if you find a sine that's bigger than 1, you can stop right there, because there's no physical beta that will correspond to that. So in this case, we have no solutions. This triangle does not exist. So that's the law of sines, and as the name suggests, there's also a law of cosines. So let's have a look at that one as well. So the law of cosines comes in basically 3 varieties, and let's look at the general form of the formula a little bit. So one distinguishing feature is that the law of cosines has 3 sides plus 1 angle. So each variant has always says something about 3 sides and 1 angle. So for instance, let's take the first one. We have A, B, C, and then the angle alpha, and then so on. The other laws have B, A, C, C, A, B, and beta or gamma. So 3 sides, 1 angle. And it's good to keep in mind, if you have to apply that formula, you can only do so if you know 3 sides and 1 angle. So the proof of this formula we will skip. But again, I can show you the brief outline of this. If we have our triangle alpha, beta, gamma with sides A, B, and C, what we can do again is drop a perpendicular like this to make it into 2 right angle triangles. Then we call this H, this side X, and this C minus X, X, like so, like so. And then what we can do is we can actually use Pythagoras' theorem and variance in those 2 triangles. Actually, let's maybe do one case together, because it's actually quite an involved proof. So let's do the case here, case alpha less than 90 degrees as shown on the figure. So here I will partially skip it. So with what I've drawn on the figure, if I call, let's call this triangle 1 here. If I go look in triangle 1, what do I know? Well, first of all, Pythagoras tells me that x squared plus h squared is equal to b squared. So this side plus this side, the squares of that is equal to the hypotenuse squared. And I also know that cosine of alpha is equal to x divided by b, or in other words, x is equal to b times cosine alpha. And it's this form that we'll use, as well as this expression. So we have 2 things here, and let's go and have a look at triangle 2. So what do we know about triangle 2? If we again use Pythagoras' theorem, now we get that c minus x squared plus h squared is equal to a squared. And then if we work it out, we get c squared minus 2cx plus x squared plus h squared is equal to a squared. And now I use the formulas that I derived earlier. So let's actually give them a nice color. Let's call this the blue formula, and this the golden formula. Then what I can do is I can use the blue formula on this, and the golden formula for x, gold, yeah, I can use that here. And then if I make those substitutions, I have that c squared minus 2c b cosine alpha. So that's, there's gold, that's x, plus x squared plus h squared is b squared, that's blue, and this whole thing has to be equal to a squared. And you see where this is going. If I clean it up a bit and I bring everything to the right side, I get that a squared is equal to b squared plus c squared minus 2bc cosine alpha. The tricky thing is that this is only one of the cases, so there's 2 other cases. Case 90 degrees for alpha then basically this becomes a right angle triangle, and then you can use Pythagoras. And case bigger than 90 degrees, then this becomes an obtuse triangle, and then you have to draw different right angle triangles. So in that case, if you want to do this by yourself, then you will have to extend one of the sides and do a similar construction as what we did for the sine formula. So you can check this for yourself if you're interested. And if you have any questions, you can reach out to me and I can help you out if you're stuck. So cosine formula, also very important formula in general triangles. So let's see a couple of examples and play with it a bit. So let's first do an example where the numbers are worked out. Take our triangle, we have alpha, beta, and gamma, and this side is 5, 8, and 12. And what we want to do here is we want to find alpha, beta, and gamma. So let's start maybe with alpha. So since I have 3 sides and I want to find one angle, cosine formula is perfect for that. I have a squared is b squared plus c squared minus 2bc cosine alpha. And if I rewrite that a bit, that becomes cosine of alpha is equal to b squared plus c squared minus a squared divided by 2bc. And now all I have to do is I have to plug in the values. So this right here, that's a, this is b, and this is c. So I get 12 squared plus 8 squared minus 5 squared divided by 2 times 12 times 8. And if I calculate that, I get about 0.95. And from that, I get that alpha itself is equal to 18 degrees. There's no ambiguity here. If you were to, well, if you take minus of this angle, the cosine would stay the same, but negative angles are not physical in triangles, so this is the only solution. I will let you do beta and gamma yourself, and you have to use the other cosine formulas, and you should get that beta is approximately 29 degrees and gamma is approximately 133 degrees. And then last, let's do a couple of problems that are maybe a bit more involved. So for the first problem, I'm given 3 sides, so I know that my side B is 2 times square root of 3, my side C is 3 square root of 2, and my angle gamma is 60 degrees. And so now if we draw this in a triangle like this, I have gamma 60 degrees, C is 3 square root of 2. I have beta, which I don't know, and I have alpha, which also I don't know, but here I have b 2 times square root of 3 and then unknown a. So these are the elements, and what I want to do is I want to find alpha. So what I'll do is I'll pause for a couple of seconds to give you the chance to pause the video and try this problem. And after you've given it some thought, you can come back to the video and compare your solution with mine. Okay, so I hope you had the chance to look at the problem a bit in detail. So let's see what we can do with this triangle. So the first thing to note is we have one side here that we know everything about. We have c is square root of 3 and we have gamma is 60, so that suggests using the sine formula. So in particular we have sine gamma divided by c, and given that we also know the value for b, let's focus on the angle beta first. Beta b. So you might say, well, hey, it's alpha that I have to calculate, not beta. But sometimes you have to work a little bit indirect. If we can calculate beta, then we know two angles of the triangle and we can find the third one. So let's plug in and see where this goes. So I have sine beta is equal to b over c sine gamma. And then plugging in the values, I get 2 times square root of 3 divided by 3 times square root of 2 sine of 60 degrees. That's great. That's a value that we know. It's square root of 3 divided by 2. And if you simplify this, you'll get square root of 2 divided by 2. So we're again in a situation where we have sine beta equal to some value that we know. So what does that tell us about beta? Well, beta can either be 45 degrees or beta can be 135 degrees. Both of those have sine value equal to square root of 2 divided by 2. If you stick with beta is 45, then what does it tell you about alpha? Well, alpha is 180 minus 45 minus 60. So that alpha is equal to 75. And here on the other side, beta is 135 degrees. I claim that that's again an unphysical solution, because if you think a bit about beta plus gamma, that's 135 plus 60, that's 195 degrees. This is already bigger than 180 degrees, so that's impossible, because it means that alpha would have to be negative. If alpha plus beta plus gamma is equal to 180, then if two of them are already bigger than 180 degrees, that doesn't work. So this again is a unphysical or an impossible solution, and we're left with alpha equal to 75 degrees. Okay, so let's do one more problem like this. So for the next problem, the statement is a bit more involved. So here, we don't know the size of the triangle, but we know their proportions. So if A relates to B and B relates to C as 4 relates to 5 and 5 relates to 6, then prove that the greatest angle in the triangle is twice the size of the smallest angle. And if you're not familiar with this notation, this proportionality, what this means is that A divided by B is 4 over 5, B divided by C is 5 over 6, and A divided by C is 4 over 6. So again, I'll give you a couple of minutes to play with this. You pause the video and you can rejoin me when you're ready and you want to compare your solution. Okay, so I hope you had a chance to look at that for a bit and make some progress. So let's draw the triangle. Alpha alpha, beta, gamma, A, B, C. And now, what do we know about the triangle? What can we put in there of values? Nothing. There's not a single value that's given to us, so this is quite a different problem. So let's play a bit with what we have so that we can see a bit where we have to end up. And let me first start with these proportionality relations that I have on top. So what these tell me is that if I work this out, I get that A is 4, 5, B, and similarly B is equal to 5 divided by 6, C. So from that, it follows that A is less than B, and B is less than C, and also that the angles on the other side correspond to the same progression. So alpha is less than beta is less than gamma. And that's why I tried to draw the figure in such a way that that looked a bit similar. I don't know how well that worked. So this is good because now we can write down what we want to prove in mathematical language. So we want to prove that gamma is 2 times alpha. Okay, it's always good to have a mathematical expression to focus your thoughts. So now, given that we know nothing about the sides except their proportions, let's brute force things a little bit. So what I can do is I can write the sides as a multiple of some value k that I don't know, which is a real number. So let me show you what I mean by that. I can write A equals 4 times k, B equal 5 times k, C equals 6 times k. And I don't know k, but if I change k, what I do is I expand the triangle and I contract it, but I don't change the angles. And if you go back to our proportionality formulas, if you divide a by b, you get 4 over 5, and k just drops out. So k is a degree of freedom that we know is there, and we're going to take it along in our computations, but eventually we're going to see that it doesn't matter for what we want to prove. Okay, so now let's start, and let's try to say something first about the angle alpha. So for alpha, I can use the cosine formula because again, now I have 3 sides and I know cosine of alpha. If you massage the formula a bit, you get b squared plus c squared minus 2, oh, sorry, it's not correct, minus a squared divided by 2bc. And if I substitute what I've just found, I get that that's 25k squared plus 36k squared minus 16k squared divided by 2 times 5k times 6k. Okay, so this is already a nice result because I see I have this k squared here, and I have a k squared, k times k in the denominator, so they all drop out against one another. So can cancel this, cancel this, cancel this. And then if I simplify the fraction a little bit, I get that this is 45 divided by 60, and that's equal to 3 over 4. So now let's say something about cosine gamma, because that's the other angle that we care about. Now for cosine gamma we have the same formula, one of the other trigonometric cosine formulas a squared plus z squared minus c squared divided by 2ab. So again, you substitute a, b, and c in there, and you simplify a little bit, and you should end up with 1 over 8. So that's good. Now let's see if we can get from those two values to gamma equals to 2a. There's a double angle in here, so I'm going to use my old friend, the double angle formula. Which says that cosine 2 alpha, and I'm going to use the variant of the formula that has cosine of alpha in it because I know cosine of alpha. So this is 2 cosine squared alpha minus 1. And I know that this is 2 times 3 over 4 squared minus 1. I just calculated that value. And now I can simplify that a little bit. And let me put it down below here. If I simplify this, I get that this value is equal to 1 over 8. And hey, this is looking pretty good now because 1 over 8 here, 1 over 8, we just calculated that's cosine gamma. So we end up with that this whole expression is cosine gamma. So what can we conclude from that? Well, cosine 2 alpha is cosine gamma, and as a result 2 alpha is equal to gamma, and that's precisely what we wanted to